Today we'll be presenting Group 2's Robot Inspector design for the MECH 4806 Winter 2021 semester. Detailed bridge inspections occur at least twice a year in Ontario to ensure they remain fit for service and to monitor defects, cracks, and flaws. The industry standard method of inspection is using non-destructive testing, and one of the most common techniques used is ultrasonic testing. Ultrasonic testing uses the pulse echo technique, where a piezoelectric probe sends and receives acoustic bursts through the test material. The burst travels to the material and bounces back when it reaches a defect or the bottom surface. The time and intensity of the reflected signal is used to determine the presence, depth, and size of defects.
The overall mechanical design for the robot utilizes a tracked vehicle with a large permanent magnet that will allow it to drive on beams in any orientation. The two tracks are individually controlled by two motors that will allow them to be used for both steering and driving the robot as it moves along the beam. On the back of the robot, a small plate is dragged along the surface of the beam and is held in place by two springs. This plate contains all of the control electronics as well as a servo that will be used to sweep the sensor arm across the beam, allowing the full width to be inspected in a single pass. The applicant used for ultrasonic testing will be locally dispensed by nozzles on the sensor arm. The applicant will be stored in the blue reservoir and will be dispensed via a piston, stepper motor, and rack and pinion system, which are all contained on the main body of the robot.
This is a crack detection and sweeper arm Tinkercad model. If I start off the simulation here, now that it's ready, you can go ahead. Button 1 here controls the calibration, so when that's pressed, it restores the current distance and stores that as the beam thickness. 4 and 5 control recording on and off, and 7 and 8 control if the sweeper arm is moving or not. So if I try to record without doing any calibration, I get error and tells you it requires calibration. So I can turn that recording off and then press 1 to calibrate. It calibrates the beam thickness, and then I can start recording. And if I move the signal to come back faster, it means that it's a crack detected before it reaches the end of the beam and the signal bounces back. And so it gives an error, and if I move it further away, no error is given. And then this is the sweeper arm. I can turn the sweeper arm 7 and rotate between 0 to 90 degrees and then back again. And if I press 8, it'll turn off. I can turn it back on again. And if the recording is turned on and the crack is detected, it'll give you the location of the crack, the depth of the crack, and the location is determined based on the position of the sweeper arm. And I can press 8 to stop the sweeper arm, and then I can press 5 to stop the recording. And that's all the basic functions.
The motor driver, which is the L293D motor driver H-bridge used in this circuit, is the key to operate and control the DC motor's speed and direction of rotation. In this electrical circuit, an UNO R3 is implemented with the H-bridge circuit to control the operation of two DC motors, which will control the treads. A 9-volt battery is hooked up to the circuit to provide power to the DC motors, and an infrared sensor is also implemented to receive signals from an IR remote, an infrared remote. This circuit was designed so that if I start the simulation, when the back button is pressed, the motors will rotate in the reverse direction at full speed, and when it is clicked again, it will stop. When the forward button is clicked, the motors will rotate in the forward direction at max duty cycle, and when it is pressed again, it will stop as well.
This is the Simulink block diagram for one of the two drive motors on the robot. The plant was constructed using Simscape driveline and electrical. The left side implements the electrical parts of the plant, including the PWM control and the H-bridge. The right side implements the mechanical subsystem of the motor. The block diagram was also implemented in discrete time domain using zero-order hold blocks. And this allows us to evaluate the effect of sampling on the controls. Here are the results from testing at different sample times. As the sample time decreases, the oscillations decrease in amplitude and increase in frequency. Additionally, the system response approaches that of the continuous time domain.